Hey everyone, Mike from Arnold Tutoring here. We've got a good power series question that I'm going to walk through. So what does the question ask for? It says find the interval of convergence for the power series. We have the sum as n goes from 1 to infinity of n times x minus 4 to the n over 3 to the n times n squared plus 1. So a lot of n's and x's and summation formulas going on there. How do we solve for this? First of all, interval for convergence, interval of convergence. What does that mean? Well, we notice that power series, as opposed to just regular series, which have a bunch of n's and we have to figure out whether they converge or not, power series actually have this variable x in there, which we're primarily concerned about. So we have x minus 4 to the n. What the interval of convergence is looking for is we need to use all of our different rules that we know about series to say, okay, if x takes on these certain values, then this series will be convergent. Versus if x takes on other values, that would make the series divergent. So we kind of use a combination of the rules we know about general series, and then we pull the x in, usually to create an inequality, which solves for the values of x that this series can take on to make it convergent. If we have no idea where to start for interval of convergence question, generally the ratio test is a good place to start. But we actually are smarter than that, and we know that the ratio test is really good here because we have 3 to the n. So this term is a really good key for the ratio test. Anytime you have a constant with the power n, or anytime you have factorials with n's in them, the ratio test is usually really good because it creates cancellation of terms. So let's recall what the ratio test is. We want to take the limit as n goes to infinity of the absolute value of a n plus 1 over a n. So what is a n plus 1? That is the n plus 1th term. So essentially you're just taking whatever is inside the series there and you're putting n plus 1 in for n, and then a n is just the actual series. So we're going to say this equals the limit as n goes to infinity. Now when we clearly these are each going to be fractions, so when we divide fractions, a n plus 1 divided by a n, we can write them as multiplied but flip the second fraction. So I'm going to write my a n plus 1 term first. So instead of n times x minus 4 to the n, it's going to be n plus 1 times x minus 4 to the n plus 1 over 3, instead of to the n, it's to the n plus 1 times n plus 1 squared plus 1. Now we're going to multiply that by the reciprocal of a n because we're dividing it, so what you do when you divide a fraction is you just flip it. So it's 3 to the n squared plus 1. Again, we're just putting in n here, so it's just the term, n times x minus 4 to the n. And it's the absolute value of all that. Okay, so why was this so helpful? Well, because 3 to the n is our real issue, and we can see that we have 3 to the n on top, and 3 to the n plus 1 on the bottom, so that means that this can completely cancel out and we're just left with 1, 3 on the bottom. So we have the limit as n goes to infinity of the absolute value of n plus 1 times n squared plus 1 times x minus 4 to the n plus 1. On the bottom, we've got that 3 left over because we had 3 to the n on top, 3 to the n plus 1 on the bottom, so that means there was one more 3 on the bottom. And then we still have everything else. So I'm actually going to expand this bracket. So it's n squared plus 2n plus 2. And we have an n here as well. X minus 4 to the n. Absolute value. Then, just like we canceled to leave only 1, 3 on the bottom, we have the same thing with our x minus 4 terms. So we have x minus 4 to the n plus 1 on top, x minus 4 to the n on the bottom. We can cancel that, and we're just left with 1 x minus 4 on top. So I'm going to rewrite this as the limit as n goes to infinity. The absolute value of, if we expand this out, we will have n cubed plus n squared plus n plus 1 times the 1 left over x minus 4, sorry about that, over 3n into n squared plus 2n plus 2, because the x minus 4 to the n is gone on the bottom, and it's the absolute value of that. Now we have that x minus 4 on its own. We know from our rules of taking n to infinity that we only have to worry about the highest term. So the highest term in the top is n cubed, the highest term in the bottom is 3n cubed if we were to multiply this out. So we're just going to be left with 1 over 3. So this is equal to the absolute value of x minus 4, that stays there because there's no n involved there, over 3. There's the 1/3 in front. Again, you could work it out in more steps, but we know as soon as we're taking the limit to infinity, we only have to worry about the highest term in the numerator and the denominator. Okay, great. So this is kind of the simplified ratio test, but what does the ratio test say? Well, it says when you take that limit to infinity of a of n plus 1 over a of n, if it's less than 1, it's absolutely convergent. And since we're looking for the interval of convergence, so those x values that make this whole thing convergent, we want this whole ratio to be less than 1. Now we just solve it, so we can say x minus 4 is less than 3, because I just multiplied the 3 up. And this gives us an interval. If we run it through twice, the first way is just drop the absolutes, and we say x minus 4 is less than 3, so x has to be less than 7. The other way is to run the negative through, and we say negative x plus 4 has to be less than 3, so x has to be greater than 1. So our interval of convergence, at least where we start, is from 1 to 7. Now, this is the most important part. So again, we said, okay, we can run the ratio test, and we know that the ratio test proves absolute convergence if it's less than 1. We simplify the whole thing. We got it down to x minus 4 over 3. We set that to less than 1, and we got this interval. We're almost done the question, but that doesn't tell us what happens at the endpoints. So we've said for sure between 1 and 7, but since this is just a less than sign in the ratio test, it's not less than or equal to, we actually have to test the individual endpoints. So we have to test 1 and test 7. So I'm going to erase here, and then we'll actually plug those into the original and see if they work. Okay, so just to recap, so far we've said for sure when x is between 1 and 7, this power series is convergent. Now we want to test at those endpoints. So at x equals 1, all you have to do is sub 1 in for x into the power series. So we get the power series from n equals 1 to infinity of n. Instead of x minus 4, it's 1 minus 4. So that's minus 3 to the n. So I just plugged 1 in for x here. 3 to the n. Nothing changes on the bottom because it's just n's, there's no x's. Now we have to be a bit creative about how this simplifies. Negative 3 to the n over 3 to the n. Well, we can say this is the sum from 1 to infinity of, I'm going to take out a negative 1 to the n there. We're left with n. Then you're just left with 3 to the n, positive 3 to the n, over your positive 3 to the n, n squared plus 1. So our 3 to the n's can cancel, and we're just left with n over n squared plus 1 times negative 1 to the n. Now, again, we have to use our skills with general series. This isn't a power series anymore, it's just a series. The most common and what should jump out at you is the negative 1 to the n, so we can use the alternating series test. The alternating series test says that if it's decreasing, so clearly since we have the higher power on the bottom and just n on top, n over n squared plus 1 is decreasing. We can prove it by showing n plus 1 over n plus 1 squared plus 1 is less than or equal to n over n squared plus 1. You could work that out to show that. But clearly it is decreasing. If you think about the first term, when we put 1 in for n, it's 1 over 2. The second term, so 1 over 2. The second term, when you put 2 in for n, is going to be 2 over 2 squared plus 1 is 5, clearly we're getting smaller, right? This is 0.5, this is 0.4. Okay, so that's good. We know it's decreasing. The second test for the alternating series is if the limit as n goes to infinity of n over n squared plus 1 equals 0, and yes, it does. So by the alternating series test, we know that this series, which was again the series when x equals 1, is convergent. Great. So now we can update our interval to not only say it's between 1 and 7, but we can put a square bracket around 1, because we just proved that at 1, at only point where x equals 1, the series is also convergent. I'm going to pause, erase, and we'll do the exact same thing for 7. Okay, we're nearly done. Again, this is a question that's going to be worth a lot of marks, which is the nice thing. So now we want to test at x equals 7, because that's the other endpoint we haven't tested yet. We've proven it's convergent at 1 and between 1 and 7. Now we just test 7. So just like before, we're going to input 7 in for x and then see which test we can use. So 7 minus 4 is 3 to the n over 3 to the n squared plus 1. Now, without even factoring, we can cancel our 3 to the n's. And we're just left with the sum from 1 to infinity of n over n squared plus 1. So here we can't use the alternating series test because there's no negative 1 to the n in front, so it's not changing signs. We could try ratio test, but there's no constant to the n and no factorials. But what we hopefully we do see is that there's one higher power on the bottom than on the top, which means we can easily integrate this function. So we're going to use the integral test. Integral test. So all we have to do is take an improper integral. So I'm going to say it's the limit as t goes to infinity of 1 to t, and we get 1 to t because our series is going from 1 to infinity, of n over n squared plus 1 dn. This equals the limit as n goes to infinity of ln of n squared plus 1. If you can't see this, over 2. If you can't see this right away, you can do u substitution, where u equals n squared plus 1, the bottom, and then you would easily see that we'll get a ln function here. Again, we can check this by taking the derivative and making sure we're good. So the derivative of this is 1 over n squared plus 1 times the derivative of what's inside, which is 2n, then you're dividing by 2. And we're still taking this from 1 to t. So finally, this is the limit as n goes to infinity of ln of t squared plus 1 minus ln of 1 squared plus 1 over 2. Clearly this is going to go to infinity when we place infinity in here for t. It's getting very, very big, so this equals infinity. So the improper integral diverges because infinity isn't a number. So the improper integral diverges, and so does the series. So you could say by the integral test we proved that the series diverges, so we know that it is divergent when x equals 7. So our final answer is what we got written here. 1, 7. 7 has a round bracket around it. That wasn't very good. 7 has a round bracket around it because it is divergent there, but it is convergent at 1. So this is your final interval of convergence. Again, that took quite a bit of work, but it'll be worth a lot of marks. Interval for convergence, if it's not clear what to do, ratio test always works well to get your interval based on the inequality that you'll get from the ratio test. But then don't forget to test the endpoints individually by subbing them in for x and then using the appropriate test again. Hopefully this is helpful. You can always email info@arnoldtutoring.com with any other questions. Thanks.